So the next speaker is Ryan McKinnon from the Massachusetts Institute of Technology in the field of physics. His advisor is Mark Vogelsberger, and his practicum is at Lawrence Berkeley National Laboratory since 2015. Let's welcome the speaker.
Okay, all right, thank you. So I'm going to talk about some of my work in astrophysics, specifically in the field of galaxy formation, where we try to model how galaxies in our universe first form and then how they evolve in time. And I know that not everyone has a background in astrophysics, so I'll start off with a little bit of motivation and a quick primer on what you need to know about this field and about some of the computational challenges that we're up against. And so I'll start with this visual representation of what a typical galaxy looks like. And I want to make the point that these systems are very large. So we're talking about tens of thousands of light years across. And towards the center of these galaxies, you have a concentration of stars that emit light. And ultimately, that light escapes the galaxy and reaches us here on Earth, where we can detect these galaxies with telescopes. But there's also a variety of other material in these galaxies around the stars, and it comes in both fluid and solid form. So there's a very diffuse gas that exists in this galaxy, and that gas, of course, obeys hydrodynamics. And there are also a lot of small solid particles, what I'll call dust grains, that coexist alongside that gas. And then these dust grains are quite effective at blocking and scattering stellar light inside of these galaxies. And so this gives you a picture of one galaxy, but we can also think about large populations of galaxies on cosmological scales. And so here on the right-hand side, we're looking at results from a recent state-of-the-art simulation simulating a large population of galaxies simultaneously. And the idea is that when we talk about galaxy formation, we're talking about something that inherently is very much a multi-physics and multi-scale problem. So you have gravity that acts on very large length scales, hydrodynamics that's much more local, acting on smaller length scales, and then a range of other physical processes that are more specific to astrophysics. And I don't have time to get into all of those here today, but I'll focus on the one that's third from the bottom, the physics of these small solid dust grains in galaxies. And so just to make this a little bit more concrete, here we're looking at some images of the sort of compounds that are thought to make up interstellar dust grains. So we're talking about things like graphite or iron and magnesium-based compounds. And these particles typically range in size anywhere from a few nanometers to a few microns. So they cover a few orders of magnitude in size. And the key point is that these dust grains contribute very little to the overall mass in a galaxy. So there's a lot more fluid gas than there are solid dust grains. But these dust grains are very effective at blocking stellar light. So something like 30% of the light in a galaxy ends up getting scattered and reprocessed by these particles. And so anytime we want to worry about the coupling between solid particles and a fluid, there are certain physical processes that we need to take into consideration. And one of those is a drag force. So that's sort of schematically illustrated here. So if you imagine having some ambient gas in blue with some sort of non-zero temperature for the gas. So these gas atoms have random motion. And if we place a dust grain at the very center in red and give it some velocity pointing to the right, over time, this dust grain will undergo a whole bunch of collisions with the gas atoms and feel an effective drag force pointing to the left, slowing this dust grain down. And what this means mathematically is in your equations of motion for dust and for gas, you get an equal and opposite force, and this drag force is linear in the relative velocity between dust and gas components. So if you have very large difference between dust and gas velocities, you get a strong drag force. And if the dust and gas are much more closely coupled, then you get a small drag force. And without getting into too much of the mathematics, I'll say that you can derive a time scale over which this drag force acts. And this stopping time scale is a function both of dust grain properties, like the size of a dust grain, A, and also gas properties like gas density, rho sub g, and the sound speed, c sub s. So for example, if we increase the gas density around these dust grains, we're increasing the rate at which these dust grains undergo their collisions. And so this results in a stronger drag force or a shorter stopping time scale. And so in our simulations, as I'll get into in the next slide, we model dust grains using simulation particles. And when you take this kind of a particle-based approach, you need to rely on interpolation techniques and kernel smoothing to estimate things like local densities. So for example, on the left-hand side, suppose I have some particle distribution and I want to estimate what the density is at the very center where there's the red circle. One simple thing to do would be draw some imaginary sphere around that point, sum up all the mass inside of that sphere, divide by the volume, and then that gives you an estimate of what the density is there. And you can actually make this more complicated by employing non-constant weighting functions. So you can weight the particles that are close to the center a little bit more and weight the ones that are further out a little bit less. But this gives you a sense of the kind of interpolation techniques that we use in our work and that are used in a variety of other fields, including SPH, smooth particle hydrodynamics. And so ultimately, we want to be able to implement our equations for dust and gas dynamics in a simulation code. And the code that I'll talk about here for solving hydrodynamics is called AREPO. So it was developed by a researcher over in Germany that we've worked with, Volker Springel. And first, I'll demonstrate its capabilities for just a hydrodynamical test problem, in this case in 2 dimensions, a Kelvin-Helmholtz instability. So the setup here is pretty simple. We essentially have 2 fluids on top of each other, moving with some sort of horizontal shear from left to right. And then we introduce some vertical perturbation, and you can see these characteristic swirls that start to form. And for those in the audience that deal with hydrodynamics, I'll mention that AREPO is solving hydrodynamics using a finite volume scheme. So this is good for physics applications because it helps us to ensure conservation of mass and momentum. And the mesh that it's solving hydrodynamics on is generated by a Voronoi tessellation of space. So here in 2 dimensions, but more generally, it can be done in 3 dimensions. And then that mesh is allowed to move with the local fluid velocity. And this gives a property known as Galilean invariance, which is useful in astrophysics. And it basically means that the laws of physics are invariant under boosts in reference frame if you change your velocity by some constant amount. And so a lot of my work over the last few years has been spent developing methods in AREPO for accounting for dust dynamics. And we do that not using the mesh, but actually using simulation particles that exist on top of this mesh. And so I'll demonstrate one example coupling between dust and gas here in a standard hydrodynamical test problem called the SOD shock tube. So this is a 1-dimensional problem where the initial conditions for gas and dust are pretty simple. So on the left-hand side, we're looking at density profiles as a function of this one spatial component. And the idea is that on the left half, we have a very high density, then we have a jump discontinuity, and on the right-hand side, a much lower density. And so as a result, the gas here in red wants to hydrodynamically expand from left to right. And so you can see actually 2 discontinuities in the gas start to form. And then the dust in this simulation is coupled to the gas through a drag force. And sort of in both cases, on the left-hand side where I have a weak drag force, and on the right-hand side where I have a stronger drag force, qualitatively in both cases, the dust tends to be dragged by the gas from left to right. And you can see that as we increase the strength of the drag force, we're really increasing the coupling of the dust and gas to the point where their density profiles look very similar. Now, I mentioned also earlier that the strength of the drag force depends on grain size, and it's important to note that dust grains change in size over time in galaxies. So they undergo a whole lot of collisional processes that can shape the sizes of these dust grains. And that's something that's illustrated here on this schematic. And I'll draw your attention to the top 2 panels where dust grains are given by the little red particles and gas atoms by the blue circles. And the idea here is that dust grains can undergo collisions with other dust grains or with gas atoms. And loosely speaking, if these collisions happen at high relative velocity, then the dust grains tend to break apart and shatter into many small grains. And if the collisions happen at much lower relative velocity, then you can get dust grains that sort of stick together, and you end up with fewer but larger dust grains. And unfortunately, I don't have time to get into all the details of how we implement these sorts of collisional processes in our simulation code. But I'll say at a high level, it shares a lot of similarities with fields that deal with population dynamics. And one of the well-known equations in this field is called the Smolkowski coagulation equation. And it's basically telling you how the density n of particles of some size x varies in time. And this integral differential equation basically has two terms. You have, on the one hand, a consumption term telling you how grains of some size x get collisionally destroyed or consumed in collisions with other particles. And then the other term is telling you how you can produce grains of size x by colliding grains of size x minus y and y for some suitable grain size. And so it's basically a bookkeeping, an accounting of all the ways in which grains can be reprocessed in size. And it's useful not just in astrophysics, but actually if you look at the literature, you'll find papers that talk about this equation in statistical physics and surface physics and numerical analysis. And so we can take this model for dust grain dynamics and the evolving sizes of dust grains, and we can actually apply it to galaxy simulations. And so here I'm going to show a simulation we ran recently of one individual galaxy. And so from left to right, we're going to look at projections of gas density, so fluid density in the galaxy, stellar density, and then on the right-hand side, the density of these solid dust grains. And from top to bottom, face-on projections and then edge-on projections in this galaxy. And so our initial conditions here are essentially a ball of gas with some angular momentum along one direction. Over time, that gas then spins up into a disk, and the gas starts to cool and become denser. Then it forms stars, and then over time, those stars produce dust grains, and those dust grains then evolve in time in the galaxy. And these sorts of simulations allow us to make predictions for where dust is in the galaxy, how it evolves, and how the sizes of these dust grains change in time. And so I won't have time to get into some of the detailed astrophysical predictions particularly, but I'll say at a high level, one thing we can do with these simulations is essentially toggle on and off different aspects of physics, different aspects of our treatment of dust grains to try to understand which physics most strongly affects how these galaxies evolve. So for example, on the left-hand side, these three colored lines are different variations of physics, and we're looking at the total dust mass as a function of time in this galaxy. On the right-hand side, we're looking at a breakdown of the dust mass into grains of different sizes. So these are essentially probability distributions telling you whether, in the case of these red and green models, you have a lot of large grains and fewer small grains, or in the case of this blue model, our full physics model, whether you have a lot of small grains and fewer large ones. And if you're curious about some of the astrophysical predictions that we can make, please come talk to me afterwards. And then with that, I'll just try to wrap up and say that if you remember nothing else, you can remember that galaxy formation is complicated. It's definitely a multi-scale problem, especially when you consider how solid dust grains interact with the fluid gas in a galaxy. But hopefully, some of the methods and the simulations that I've introduced here give you a sense of the kind of predictions that we can make about galaxies that otherwise are pretty far away. So I'll stop here, and I'm happy to take any questions. Thanks.